morning, students. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So, in the previous session, we have studied about shafts design. So, in this session, we will see problem solving, how to solve the given the shafts design. So, the shaft design based on two cases. One is strength basis and the second one is torsional rigidity basis. Already you know. So in this and strength basis again classified into four types. First one is when the shaft subjected to bending movement, and the second one when the shaft subjected to torsion, and third one combined the bending movement and the torsional movement problem. So we will see the fourth one. So in addition to these two, axial load will act. So one by one we will see. So in first case already we have studied in the last session. The second one, shaft subjected to bending moment only. So in this, when the shaft subjected to bending moment, the maximum stress or tensile or compressive is given by the bending equation. So what is that equation? So here the bending moment equation is m by I is equal to sigma b by y. So here m is the bending moment and I is moment of inertia, and bending stress sigma b, and y is the distance from neutral axis to the outermost fiber. So actually this equation comes from m by I is equal to E by R is equal to F by Y. This is the bending equation. So in this, so we can write this one, the bending stress or F or sigma B. So take these two. So you can write the bending moment equation like this: m by I is equal to sigma B by Y. So bending moment M and I moment of inertia of cross-sectional area of the shaft. So next sigma b, and d is y is the distance from the neutral axis to the outermost fiber. So we know that for a round solid shaft, the moment of inertia is 5 by 64 into d to the power of 4. So here the d is shaft dia. Y is equal to d by 2. This is the distance from the neutral axis. So substituting these two values in first equation, in equation 1, m by I is equal to sigma b by y. So substitute. So here m and I in place of y, substitute 5 by 64 into d to the power of 4. So and sigma b. So keep this keep the bending stress value like this, the sigma b, and then the y is d by 2. So finally, after simplification, we will get the bending moment equation is m by 5 by 32 into sigma b into dq. So whereas in the torsion case, torsion is equal to twisting moment or torsion is equal to pi by 16 into tau into dq. So in this, we are considering bending moment only. Why? Because the case is when the shafts are subjected to bending moment. Next one, from this equation, the diameter of the solid shaft may be obtained. So that is a solid shaft, and also you know that for hollow shaft the moment of inertia and then y value, again substitute in the previous equation, we will get another one more equation. So by using the previous equation, so that is m is equal to 5 by 32 into sigma b into dq. So in this substitute all values, so we will get d. So in design problem, they will ask design of a shaft. So means we have to find out the diameter when the shaft is subjected to bending moment. So similarly, this one is for a solid shaft. In case of hollow shaft, it has outer diameter and inner diameter. So consider the shaft. So this is inner diameter and outer diameter of the shaft. Hollow, DI and D naught. Clear? So in this case, the moment of inertia I is equal to 5a64 d naught to 4 and di to 4. So you will get 5a64 d naught to the power of 4 and 1 minus k to the power of 4. You may be written like this. Kb. So here k is ratio of inner diameter to outer diameter. Inner diameter to outer diameter. So substitute this k value. So we can write the finally 5/64 the d naught to the 4 into 1 minus k to the power of 4. Now again substituting these values in equation 1. So we will get the bending moment equation. So m is equal to 5/32 sigma b d naught cube to 1 minus k to the power of 4. Clear? This is for hollow shaft. So the final equation m is equal to 5/32 to sigma b, that's bending stress, into d naught cube outer diameter multiplied with 1 minus k to the power of 4. So here k is di by d naught. So from this equation, you may calculate the outer diameter of the shaft. So d naught may be obtained. If you know the d naught, and then easily you can calculate inner diameter of the shaft. So now we'll see one problem. So a pair of wheels of a railway wagon carries a load of 50 kilonewtons on each axle box, acting at a distance of 100 mm outside the wheelbase. The gauge of the rails is 1.4 meter. Find the diameter of the axle between the wheels if the stress is not to exceed 100 megapascal. So here, given, first write down the given data, the load is 50 kilonewtons and the length is 100 mm. And x is, the length between the two rails is 1.4 meter. Sigma b is 100 megapascal converting to Newton per mm square. So 1 megapascal is equal to 1 Newton per mm square. So that you can write the 100 megapascal is equal to 100 Newton per mm square. So for this problem, first you have to draw the schematic diagram. So that is a free body diagram of for a given problem. So the pair of wheels of a railway wagon carries a load. These are two rails. The shaft is arranged like this. Carries a load of 50 kilonewtons on each axle box. And at each axle box, the load is 50 kilometers acting at a distance of 100 meters outside the wheelbase. So outside the wheelbase from here 100 50 kilonewtons. Here also 50 kilonewtons, 100 distance. The gauge of the rails is 1.4 meters. Find the diameter of the wheel. So D is equal to how much? The stress is exceed 100 megapascal, not to exceed 100 megapascal. So the given problem like this. So for this problem, you have to calculate bending moment. Bending moment and then apply bending equation and finally calculate diameter of the shaft. So the maximum bending moment acts on the wheels at C and D. So C and D first to mark the point ABC, A, B, C, D. So therefore the maximum bending moment W into L. So distance load multiply with distance. Here load is 50 and the length is 50 kilonewtons and length is 100. 50 kilonewtons, 50 kilonewtons and multiply with this 100 Similarly at C, 50 kilonewtons and 100. So the maximum bending moment obtained as follows. The RC and RD reaction force as 50 kilonewtons. The bending moment at A and ends are 0. The end supports are 0. So you may write, let's again draw one figure neatly. So length is 1.4 meter. So axial diameter is D. So you can mark it A and B like this. Also you can write C and D. So 50 kilonewtons. Here also 50 kilonewtons acting outside 100 Here also 100 So reaction forces at their loads RA and RB. Will act at its support ends. So now for this diagram, calculate the bending moment, reaction forces RC and RD is 50 kilonewtons. The maximum bending moment act on the wheel set C and D. So bending moment at A 0, bending moment at C 50 multiplied with 10 cube into 100, 10 cube into 100. So bending moment at C 5 into 10 to the power of 6, and similarly the bending moment at D at B 0. These two are fixed ends. So there is no bending moment at A and the B. So let D diameter of the axis. So we know that the maximum bending moment equation. So substitute this bending moment equation in this equation. In this empirical relation. So M is equal to pi by 32 sigma B to dq. So maximum bending moment calculated from the given problem, and then sigma B already has given in the problem 100 megapascal and D unknown. So calculate D. So D 79.8 mm. So the standard diameter of the shaft is 80 mm. So always the standard diameter of the shafts are taken like this, 25 to 60 mm size in 5 mm steps. So 25, next 30, 35, 40, 45, 50, 55, 60 like this. So after that 10, 10 mm. So 60 plus 10, 60 plus 10, 70, 70 plus 10, 80. So our value comes under this category, the 79.8. So in between 70 and 80. So the final standard value have to take 80 mm. So like this need to calculate. Next, second one is shaft subjected to combined twisting moment and bending moment. So in this case, when the shaft is subjected to combined twisting moment and bending moment, then the shafts must be designed on the basis of the two moments simultaneously. So what are the two moments? So here two theories are important for subject point of view. One is the maximum shear stress theory and then the maximum normal stress theory. So by using these two theories, two movements parallelly have to calculate. So finally we will take the larger value of the calculated values. We can fix as a final bending moment. So the maximum shear stress theory or gas theory is used for ductile materials, and the normal the stress theory or Rankine's theory used for brittle materials. So example for ductile material gas theory, according to gas theory, it is used for the ductile materials. Example mild steel. Similarly, the brittle materials application, the margin maximum normal stress theory will use. Clear? So example cast iron. So here shear stress induced in the due to the twisting moment and bending stress induced due to the bending moment. The first apply the maximum shear stress theory. So maximum according to maximum shear stress theory, the maximum shear stress is equal to half into square root of bending moment whole square plus 4 tau square. So here bending stress plus 4 tau square. Sigma B is bending stress and here shear stress. So substitute the bending stress value and shear stress value. So already you know M is equal to 5 by 32 into sigma B into dq. Similarly, T is equal to 5 by 16 into tau into dq. So from this equation, the sigma B value, find out sigma B is equal to 16m by 32 32m by 32m by pi dq. So this value substitute in the previous equation. So similarly, top value 16t by pi d cube. So substitute in this equation and simplify. So we will get an equation 5 by 16 to tau max is into d cube into 2 square root of m square plus t square. This term is known as equivalent twisting moment. Square root of bending moment square plus twisting moment. So it is denoted by T suffix E. So equivalent torque. The equivalent twisting moment may be defined as that twisting moment which when acting alone produces the same stress as the actual twisting moment. Clear? So here the above equation written like this: Te is equal to square root of m square plus t square is equal to pi by 16 into tau into dq. From this expression, the diameter of the shaft may be evaluated. Now, according to maximum normal stress theory, the maximum normal stress in the shaft sigma b max is equal to half into sigma b plus half into square root of sigma b square plus 4 tau square. So, maximum normal stress theory, the maximum normal stress in the shaft sigma b max is equal to half into sigma b plus half into square root of sigma b square plus 4 is already we have calculated in the previous step. So substitute again in place of sigma b 32 m by pi d cube and in place of tau 16t by pi d cube. Clear? So we will get finally pi by 32 into sigma b max d cube is equal to half into m plus square root of m square plus t square. So the expression is known as equivalent bending moment. Is denoted by ME. ME is equal to into m plus square root of m square plus t square. So you may write like this: equivalent bending moment is equal to half into m square plus square root of m square plus t square is equal to 5 by 32 sigma b into d cube. So in this expression, the diameter of the shaft may be evaluated. In case of hollow shaft, so already you have discussed in the first or second slide. So in place of hollow shaft, in case of hollow shaft, so substitute in place of diameter, so substitute d naught cube into 1 minus k to the power of 4. So k is equal to di by d naught. Clear? So finally, we will get two values. One is by using maximum shear stress theory, and second one is Rankine's theory, normal stress theory. So the final diameter suggested by using the both theories, larger value of the two values, calculated values, we can fix as a final diameter of the shaft. So like this, how to calculate design problem when the shaft is subjected to twisting moment and bending moment. See this problem. A solid circular shaft is subjected to a bending moment 3000 Newton meter and a torque of 10,000 Newton meter. The shaft is made of 45C8 steel having ultimate tensile stress of 700 megapascal and the ultimate shear stress 500 megapascal. Assuming a factor of safety is 6, determine the diameter of the shaft. So diameter, how to find. So here the given data, first write down M is equal to 3000 Newton meter and torque is equal to 10,000 Newton meter. And the ultimate tensile stress, that is 700 megapascal, and ultimate shear stress 500 megapascal. Here factor of safety is given 6. So factor of safety value is taken 6. So here the given values, these are ultimate stresses. So need to calculate allowable stress or permissible stress by using this factor of safety. So how to calculate, you will see. So given data and then allowable tensile stress, calculate by using given factor of safety. Ultimate stress by factor of safety. So you will get 116.7 Newton per mm square. The given ultimate stress is 700. Factor of safety is 6. Similarly, the allowable shear stress, allowable ultimate shear stress by factor of safety. So 500 by 6. So 83.3 Newton per mm square you will get. So now apply two theories. Whatever we have discussed in the previous slides. First apply the maximum shear stress theory. So that is guess theory. So according to the maximum shear stress theory, the equivalent twisting moment TE is equal to square root of m square plus t square. So substitute m and t values. So we will get 10.44 into 10 to the power of 6 Newton mm. So the equivalent twisting moment TE is equal to 5 by 16 into tau into d cube. So here twisting moment value 10.41 10 to the power 6 is equal to 5 by 16 tau into d cube. So here shear stress value, already we have calculated allowable shear stress value, need to substitute. So we will get in terms of dq d and finally you will get 86 mm. The second theory, according to the maximum normal stress theory, so find out the equivalent bending moment. So equivalent bending moment equation is half multiply with inside bracket m plus square root of m square plus t square. So you can write like this also, TE is equal to square root of m square plus t square. So this is bending moment. So after substitute of the bending moment value and torsion equivalent torsion value, you will get the bending moment, equivalent bending moment is 6.72 to 10 to the power of 6. So now substitute in this equation. So we will get diameter is 83.7. So taking the larger values of the above two calculated values, the final diameter of the shaft is 86. You can say 90 according to the standard diameters of the shaft. In first case, diameter of the shaft is 86 and then second case diameter is 83.6. The larger value is 86. So what is the standard size after 80? So actually 60 to 70, 70 to 80, 80 to 90, 90 to 100. The standard dimensions, the standard shaft diameters are like this. So now after 80, so you can say 90 mm. The value 90 mm. Like this, need to calculate when the shafts are subjected to bending moment and twisting moment by using these two theories. One is the maximum shear stress theory, another one is the maximum normal stress theory. So after finding the values, the two values, so finally we will take the larger value of the two calculated values. So that is 90 mm, the final one. So when the shafts are designed on the basis of strength, so like this, have to calculate. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.